Hello and how are you? Welcome back again to this second tutorial under integration, a subsection of elementary calculus. And I am your tutor Dick Joseph Adeli. Before we begin, let's bow down in reverence for word of prayer, asking God to guide us. Father Lord in heaven, we come again unto you asking that you may teach us the second segment of integration that we want to learn about actual area calculation. Be with us, Lord. In Jesus' name I pray. Amen. Now, you have heard me alluding in the prayer that we are going to work out about calculation of areas. Now, before we go to that, let's note where we have come from, where we are, and where we are going. Now, by the end of this topic, you should be able to carry out the process of differentiation, which you know. You should be able to interpret integration as a reverse process of differentiation. Now, we are going to do that in detail. Quite some of these particulars, especially most of the time in the next tutorial, whereby we're going to be looking at application of integration. So stay tuned. Should also be able to relate integration notation to some of areas of trapezia under a curve. So that's what we're going to deal with in this tutorial. But a caution or a disclaimer: the trapezia in which we are speaking of here is basically the trapezoidal rule. So we are not going to handle directly the trapezoidal rule because we did it in area approximation, but I'm going to teach you how to be able to calculate area by the use of the method of calculus. So with that method that I'm going to give you, with the example that we're going to work out with, I beseech you, because you have prayed that God teaches us, I would like you to be faithful and honest, to go down to your work and also work out with that particular process. Not only trapezoidal rule, but also mid-ordinate rule and all the other processes that you know, so that you may compare how they come up with their answers. So that is my plea unto you. About integrating a polynomial, you know that, how to integrate, because now basically you cannot calculate area if you don't know how to integrate. You have to know how to integrate. You should also be able to apply integration in finding the area under a curve, which you're also going to do that in this particular case. We are going to also, in the next tutorial, we're going to also apply integration in kinematics. I believe you know what kinematics is. So that is basically what we're going to do. Now, actual area under a curve. How is this thing calculated, or this animal? Now, the actual area under a curve between limits is found by definite integral of a curve. What do I mean? Definite integral is basically whereby we integrate a particular function under a specific limit or under a defined limit. For example, you cannot, if you want to be able to collect people, integrating, I'm simply using the exact terms, integrating people, I'll basically say I want to integrate people of Kenya, a specific boundary, or I want to integrate people of Kisumu County, for example. I cannot just say I want to integrate people and you don't know where you want to integrate it from. That will be an indefinite integral in that dimension. So basically, calculating area, you'll have to use a definite integral. So basically, I'll have my axis so that we're able to try now and analyze a sample of graphs that we are to expect in our journey under calculus. Now, if I have a curve like that, of which I'll call this curve y is equals to x power n, now you can basically find yourself in a point whereby you want to calculate the area under this particular curve. Under the curve, I simply mean you have this curve here. Now I want to calculate anything and below that curve, and that curve that particular area must be well defined. For example, you can calculate your area between point A to point B, bound by the x-axis, or basically the line y is equals to 0. So point A and point B lie on this axis, meaning I'm calculating, I may want to calculate for the area from this particular point downwards, this whole area like this. this is the area I'll learn to be able to calculate. So how do you calculate then that area? First, we have learned how to calculate area using mid-ordinate rule, trapezoidal rule. You also know the counting technique. But in this case, I would like us to learn how to use integration. So basically, to get the area under the curve between the limits point A and point B, or basically between lines x is equals to A and line x is equals to B, you'll basically have that particular formula. You basically integrate between those two limits, whereby A is our lower limit and B is our upper limit. So basically, when we integrate, you basically substitute the upper limit and then subtract the lower limit result. We are going to look at that in detail. So please note my words with keenness so that you may be able to get more sense in the later parts. We basically substitute the upper limit first into our integral minus the result of the substituted value of A into that particular integral again. Then you work out and get the value. You'll get the value of A. But what if you introduce another line, for example, whereby now I want to calculate for the area between the curve and this particular line. So it means I'm looking for this area that I've shaded in yellow, whereby I will call that line, for example, y is equals to 3. So between those 2 points, I'll basically look for the corresponding limits, which will be C and D. What will you do for that case then? You basically integrate your function between C and D. The formula still stands the same. Now, what if you now have a curve in which it now comes, for example, in this nature, whereby you have such a thing? What will happen? Let's have such a curve. For example, here is an example of a curve. Now, for example, I just come and tell you, calculate for the area under this particular curve, for example, from here all the way to here. So calculate for the area, this area that I've shaded in yellow. What will you do? You'll basically integrate your equation of that particular curve, the equation of that particular curve, sorry for that, from this particular point to that point, and the answer that you'll get, you'll be surprised, it will be negative. Now, your negative answer, because you'll get a negative answer because it is lying below the axis, and below the axis you basically have negative values. So don't be surprised when you get negative values, because it's just like that. You have to get negative values. So because you are calculating for area can never be negative. You'll basically substitute it by a positive value. Now, what if now you want to calculate a cumulative area of this particular point? You also include this one and then this one. Now, this is where you need to be careful. How will you be able to do it? Notice I have, for example, point P there, point Q, point R, point S. So how will you do it? Did such a thing come into your mind? Integrating from P all the way to S. Now, something you need to know, that is wrong. You should not think of such a thing, because of this particular reason that you need to get. Notice we said if you are calculating the area here, it will be negative. Now, a negative answer, this one is also negative. And this one, surprisingly, it will give you positive. Not surprisingly, it's a fact. Now, imagine this. I got my below area here as, let me just get my writer pen here. Now, assuming this area below here was negative 2. That was before you eliminated that particular negative sign. Add the second area here, which is, for example, let's say 1 unit, and this other one again, negative 2. If you punch that answer, you'll get, this is negative 1, negative 3. Now imagine this is negative 3 units. But if you cumulatively add everything, you should be able to get 5 units. You can confirm that from your other formulas. So what should be done? This is how integration will work. If you basically integrate from P to S, you'll basically end up with a wrong value when and only when you have such a kind of a curve, for example, cubic graphs, whereby the curve may end up going below the axis and going above the axis and like that. So in such curves, you don't integrate from the first limit to the last limit. You basically break it down into parts. So you'll break it down from P to Q, from Q to R, from R to S, then sum all of them. That's after you have eliminated the negative sign. And this brings me to one particular rule before I give you the formula. The rule here is, before you calculate for any area by using calculus or by integrating, I've liked the word calculus, by integrating, ensure that among the steps that you are going to do before you start calculating the area or integrate or do anything, you must sketch the curve. You must sketch the curve. This is because it shall tell you the nature of the curve you are working with. For example, this one has already given me a warning that I'll end up with a negative answer, positive answer, and negative answer. You must split it down. This is what I mean. My total area will be equal to the integral of P to Q from here, and then I'll add the next, I'll add that next. Now notice this one will be a negative answer. The moment I get a negative answer, I'll be able to monitor it and drop the negative sign, because you cannot have a negative area. It will always be positive. And the same thing applies like that. So you can be able to monitor it separately. So that's something you need to be able to note. Now let's get something here. So just eliminate this 0 and 4 here just for a while. We are going to use them later. It's like I forgot to be able to type them into my animation process. Now find the area enclosed by the curve y is equals to 4x minus x squared. Enclosed by that curve, the axis and the lines x is equals to 1 and x is equals to 3. I have not read it well. Let me read it again. Find the area enclosed by the curve y is equals to 4x minus x squared, the x-axis, and the lines x is equals to 1 and x is equals to 3. Could you please attempt that question so that we may be able to exercise our mathematical skills of integration by looking for the area? Now with such a question, because we don't know the nature of the graph, we have to start by calculating, or basically looking for the nature of that curve. So I'll basically have my equation there, differentiate that particular equation, that particular function, such that I know the nature of the turning point. So in this case, I'll start by getting the x corresponding point and the y corresponding point, which will give me 4. So it means my turning point or my stationary point is 0.24. Now with 0.24, I'll go to the next level, determining the nature of my graph. I'll have the first option of using this table, of which I'll have my nature of that like that. I basically, you know how we can be able to calculate this. You basically substitute these particular functions into your derivative, such that if you substitute 1 here, for example, you'll have 4 minus 2, you get positive 2. Substitute 2, you get 0. Substitute 3, you'll end up with 6. So 4 minus 6 is negative 2. So you have that nature. Or you can use the second derivative. So that proves to us that the 0.24 is a maximum point. If I use the second derivative, I'll get negative 2. Now what is negative 2? It is less than 1. Now if we said that if any second derivative is less than 1, you think of it in terms of the maximum value, the maximum point. So that's something you need to note. Now after you have known that, let's get the x and y intercepts. We know that the x-intercept works whereby y is equals to 0. So if I substitute into my main function whereby I substitute for y to be 0, I'll calculate x to be 4 and x to be 0. And then I'll know that my points are 4, 0, and 0, 0. Finally, my y-intercept, substitute into the main function, I'll get y is equals to 0. So that means my intercepts are that 4, 0, 0, 0, and 0, 0. Now I'll draw my axes and sketch my graph. That's where the numbers now become handy. So I'll start with that point, the turning point, and then the x and y intercepts respectively. Then draw my curve. So this tells me, something. So calculate the area enclosed by the curve y is equals to 4x minus x squared, of which it is this particular curve here. So that curve, the x-axis, which is this line here, and then we have x is equals to 1, x equals to 1 comes here, and x equals to 3 here. So it means I'm looking for the area in this region. So that is the region. But the advantage here is it has not gone to this particular negative side. So we have no worry about integrating. So I'll basically integrate directly from that particular point. So I'll integrate my function from 1 to 3. So if I integrate that, you'll basically find that your area will be 22 over 3 units, square units, but the correct answer here shall be this, 7 1/3 square units. Now, why am I writing square units? Now, notice, with I know that you are used to saying that the area is usually meters, square meters or square centimeters or other things. But here we are working with units. Units is also another type of measurement of length. So basically, if you multiply the units twice, you get square units. So that is the formula that you'll have. Now, otherwise, success in your preparations. May God bless you abundantly. What I'll really want to emphasize before I go away, the same formula that you have simply done is for all particular graphs. If you have a cubic graph, all those kinds, you start by sketching the graph, check how you're going to be able to maneuver around so that you may not find yourself in trouble. May God bless you abundantly, success in your preparations.